Okay. So today we are going to start the new paper. It's May-June 2021, paper 14. Let's start with question number 1. An aqueous solution of chromium 3 contains green hexa-aqua chromium 3 positive complex ions. Okay, so these are of green color. Complete the electronic configuration of an isolated chromium 3 positive ion. Okay, so if you look at the periodic table, you will find that the atomic number of chromium is 24, which means chromium atom have a 24 electrons. But here it's a chromium 3 positive ion, which means it have a 3 electrons lesser. So it could have a 21 electrons, right? And the other thing that you have to remember is that chromium is an exceptional case where the electronic configuration is 4s1 and 3d5, the electronic configuration, and over here 4s1 3d5. And first the electrons are going to remove from 4s, so 4s becomes 0, one electron is removed from here, and from 3d 2 electrons are removed, so it is 3d3. So I have to put 21 electrons, and at the last I have to put 3 electrons in 3d3. So 1s2, then 2s2, then 2p6, 10 electrons are filled. Then after 2p6 we have 3s2, 12 electrons are filled. Then 3p6, 18 electrons are filled. Now out of 21 I have filled 18 electrons. There is no need to write 4s because there is no electron in 4s, and in 3d we are left with the 3 electrons, so it would be 3d3. Yes, is this clear to everyone? Now define the term complex ion. Okay, so an ion which is formed by a central metal atom which is datively bonded to ligands, or you can specify one or more ligands. Is this clear? Okay, let's move to the next part. So you have to remember these definitions. Chromium hexa aqua 3 ion shows some similar chemical properties with cobalt hexa aqua 2 ions. So see, they have told you that there is a similarity in their chemical properties, right? So you have to keep in mind this thing while writing the rest of the answers. So sample of hexa aqua chromium 3 are reacted separately with either OH and hydrogen peroxide, sodium hydroxide and hydrogen peroxide, or excess ammonia. Use this information and a booklet to suggest the formula of the chromium species form. State the type of the reaction taking place in each case. Okay, let me recall you when we talk about H2O2. Normally, H2O2 behaves as an oxidizing agent. Okay, normally H2O2 behaves as an oxidizing agent, and they have told you the chemical properties of chromium 3 positive ion is similar to the chemical properties of cobalt 2 positive ion. So if you recall this reaction when we added sodium hydroxide in cobalt 2 positive, what would happen that you either get cobalt hydroxide, which you can mention like this, or you can mention or write the whole complex with the 4 water molecules and 2 hydroxide ions. So with the chromium, the same reaction would occur, but chromium have a 3 positive charge. So the chromium hydroxide have a 3 hydroxide in it. So you can write in this way, or you can write the whole complex that Cr H2O3 OH3 and then close the square bracket to show its complex. Is this clear? And another important thing, when we talk about transition metal hydroxide, so none of the transition metal hydroxide is water soluble. Okay, so whenever a transition metal hydroxide is formed, that transition metal hydroxides are water insoluble, so they would form as a precipitates. So the type of reaction asked by the examiner, I may write precipitation over here. Yes, is this clear to everyone? If anybody have any question or any confusion, do ask.
Sir, why is this like a 3 H2 and 3 OH? Like not the 4 into ratio?
Sorry, can you repeat?
Why does it has like a 3-3 ratio of H2 and OH unlike the 4 into ratio in cobalt?
You are saying why we get 3 hydroxide over here, right?
Yes, and in the complex too.
Uh, okay. If we look at the chromium hexaaqua ion, if you see over here, its oxidation number is 3 positive, which is showing that chromium have a 3 positive oxidation number. Is this understandable?
Yes, sir.
When you look at the cobalt hexaaqua ion, the oxidation number is 2 positive. So it means because we know that water is a neutral molecule, it doesn't have a charge. So the cobalt have a 2 positive ion, right? Is this clear? So if you look at the reaction, let me show you from the notes, so it might be helpful for you. Where is transition? Yes, can anybody see where is transition? Electrocut here. Okay. See, here I have mentioned that cobalt 2 positive is react with NaOH and ammonia as same as copper. So let's have a look at the reaction of a copper over here with the hydroxide. See, Here you go. When sodium hydroxide is added, as copper have a 2 positive oxidation number, so here the complex that we are getting is a neutral one. Its oxidation number is 0. So two hydroxide ions are bonded to a copper to form a neutral compound. Is this understandable?
Yes, sir.
So same thing happens with the cobalt. It means when we add sodium hydroxide in it, so as its oxidation number is 2 positive, so two of the water molecules are substituted and we get a 2 hydroxide ions over here to get a neutral complex, and we can show this complex as this compound as well. But when it comes to chromium, as chromium's oxidation number is 3 positive, so now not 2 but 3 hydroxide ions would react, forming this complex where there are 3 hydroxide ions to get the neutral complex. Now is this understandable?
Yes, sir.
And these complexes or the compounds are always water insoluble. That's why this type of reaction is called precipitation. Okay. So as I've mentioned that H2 reaction with the hydrogen peroxide, as hydrogen peroxide is oxidizing agent. And if you see here, they have refer you to look at the data booklet. So we will do it later. First, let's look at the reaction with the aqueous ammonia. So if you see over here, a cobalt reacting with aqueous ammonia, all the water molecules are substituted by ammonia. Okay, it's for copper, and here is for cobalt. See, we are getting either this or either this. And if you look over here, we are using excess ammonia. So if we are using excess ammonia, it means all of the water gets removed and all of the water molecules are substituted by ammonia ligand molecules. So we are getting this complex. And as this is aqueous, this complex is also aqueous. So we call this reaction ligand substitution. Yes, is this clear to everyone? Now, let's move to the data booklet. It's an oxidizing agent. So there is a probable chance that we have to look that 1 minute. This can oxidize chromium 3 positive to some other positive state, oxidation state of chromium. So let's have a look over here. So first, we can exclude this equation because there is no chromium. Next, there are chromium 3 positive in these three equations, but if H2O2 is oxidizing agent and chromium 3 positive have to be oxidized, so I can exclude these two equations as well, because in these two equations, there is a chromium 3 positive and this chromium 3 positive in these two equations undergoing reduction. So I can exclude these two as well. So I am left with this equation where the chromium 3 positive, when undergo reverse reaction, it would form dichromate where the chromium have a +6 oxidation number. So if you look at the value of this is positive 1.33. So let me write over here. If chromium is 3 positive is oxidized to chromium 3 6 plus, then its electrode potential is positive 1.33 volt. And if the reaction would happen only when this H2O2 have a E naught value greater than the chromium, otherwise the reaction would not happen. So let's see where is hydrogen peroxide. Okay, see here we have a hydrogen peroxide undergoing reduction and its value is positive 1.77. Yes, its value is greater. So its value is positive 1.77 volt. So it means it would undergo reduction and it would oxidize this chromium to Cr2O7. So from this conclusion, we can now we actually know what product is formed. So it must be Cr2O7 2 negative, and the type of reaction is as the chromium is changing from +3 to +6. So we call it redox or oxidation. Is this clear? Yes, is this clear to everyone?
Yes, sir.
Okay. Now C part. Chromium hexaaqua 2 positive and this whole complex are both the complexes of chromium 2 and have a different colors. Explain why the colors of these complexes are different, and it's of just 2 marks. So we can just say that the difference in energy between the d orbitals is different. What does this mean? This means, for example, if water is a ligand, then in this case, if d orbitals are splitted like this and they have a energy gap of this, but when these ligands are bonded, then it might be that they are splitted like this, that the energy gap between these two are actually different than the water. So that's what this means, that the delta E between the d orbital is different for both the complexes. And why is it so? Because both the complexes have a different ligands. So now what would happen and why they show a different color? Because that the delta is different. So the electron that absorbs the energy, that is absorbed is actually the different. So we can write that the different wavelength is absorbed by each complex Hence, different color is shown. Is this understandable to everyone? Now, next part. Okay, the structure of CR. Okay, this whole complex is shown. Okay, here it is. Ethanoate ions act as a ligand in this complex. The ethanoate ligand is shown as this. Okay. So here you have a structure. So how many ethanoate are there? If you see, this is a one ethanoate. Here we have a second ethanoate. Here we have a third ethanoate. And here we have a four ethanoate. See, there are four in the formula. Water and ethanoate ions behave as different type of ligand in this complex, suggest an explanation for this statement. So what we are observing that one ethanoate ligand is forming the two dative bonds and one water molecule is forming the one dative bond. So that is the difference. And when the a ligand which forms the two dative bonds is called a bidentate ligand. So we can just state or comment on the type of these two ligands. So we can write that water is monodentate ligand, but ethanoate ion is bidentate ligand. Is this understandable to everyone? Okay, now reduce the coordination number of chromium and the geometry around each chromium atom in this structure. Okay, so coordination number is identified by the number of dative bonds or number of the bonds formed by the ligand around one atom. So if you look, let me consider this one chromium. So if you see, this is the one bond, second bond, third bond, fourth bond, fifth bond, and sixth bond. So there are six bonds. So it means the coordination number is 6. And if the coordination number is 6, then the geometry or the shape is always octahedral. Yes, is this clear to everyone? Okay, next. State the type of bond between the two atoms in chromium bond. Yes, can anybody identify? Yes. Which bond is between the two chromium atoms? Here you go.
Sigma bond.
Why sigma bond? Why don't you just justify it as a covalent or metallic or ionic or dative bond?
It's a
Sigma
covalent
bond,
bond.
it's a covalent bond. But more specifically, it's a dative bond because you see, why, if it's a central atom, then all the bonds across it must be a dative bond. That's why we are considering it as a complex. So we consider this bond as a dative bond. Okay, now next part. This complex reacts with aqueous acid to form chromium 2 positive ions. The aqueous chromium 2 positive ions react with oxygen under acidic conditions. Chromium 3 positive ions are formed. So if chromium 2 positive ions are converting into chromium 3 positive ions, the oxidation number is increased, which means it is must be an oxidation. Use the data booklet to answer the following questions. Okay. Construct an ionic equation for the reaction of chromium aqueous 2 positive ions with the oxygen under acidic conditions. Okay. Okay. So, okay, let me do the working over here. They have given us one hint, and it is that chromium 2 positive is converting into chromium 3 positive, which means one electron is lost. So we know one half equation. Now we need oxygen in an acidic condition. Okay. So first let me look at the E naught value of this one. I have written already it in the terms of oxidation. Where is chromium? So this is the equation. So for this reaction, if you see, this is the equation, right? And we already flipped it because the oxidation is taking place and its value is minus 0.41. Now, let's have a look at the equation for oxygen and an acidic medium. So if you see, you have oxygen, 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 oxygen. But here you have acidic condition and here you have acidic condition, right? So it means you can remove this and this equation. Now you are left with these two equations. But if you see, both the have a value greater than this value, right? So it means I can use any one of the equation. Whether if I use this equation, it is going to be considered as a correct. If I use this equation, this is going to be considered as a correct. But I'm going to take this one because of the greater difference. So O2 oxygen plus 4 hydrogen ions, gaining 4 electrons, forming 2 moles of water, and its E naught value is positive 1.23 volt. Okay, so it would go reduction and it would undergo oxidation. But here we have our 4 electrons, so I have to balance the equation. So I have to multiply this whole equation with a 4. Now, if I add both the equation, I will get the net equation that the examiner is talking about. So these electrons are get cancelled, and I have a 4 chromium 2 positive ion plus oxygen plus 4 moles of hydrogen, turning into 4 moles of chromium 3 positive and 2 moles of water. So this would be my equation: 4 chromium 2 positive plus oxygen plus 4 hydrogen ions plus 4 moles of chromium 3 positive and plus 2 moles of H2O. Now calculate the E naught cell for this reaction. So for E naught cell, we all are aware of the expression that what we do E reduction minus E naught oxidation. So in the in this half equation, the reduction is taking place and its E naught value is 1.23 minus here the oxidation is taking place and its value is minus 0.41. So what I'm going to get 1.65, right? It's positive 1.65 volts. Is this clear?
Yes.
No, sorry, it's 1.64. 3 and 1 gives me 4. Okay, if anybody have any doubt, kindly ask. Okay. Now let's move to question number 2. A. State and explain the observation in thermal stability of group 2 nitrates. It's very easy. First, we will state the trend, and that trend is that the thermal stability of the group 2 nitrates increases down the group because the size of cations increases due to which less polarization of nitrate ion, hence nitrogen oxygen bond in nitrate ion gets more stronger. So obviously we need a more heat to break this bond. Is this clear to everyone?
Yes, sir.
Lead 2 nitrate decomposes on heating in a similar manner to group 2 nitrates. Write an equation for the decomposition of lead 2 nitrate. Okay, so if you recall the decomposition of group 2 nitrates, it could be like this, that on heating we will get a metal oxide, 2 moles of nitrogen dioxide, and half mole of oxygen. So what we need to do, just need to displace M with Pb. So PbNO3 taken twice. It's a solid. When we heat it, we get PbO, a solid, 2 moles of nitrogen dioxide gas, and half mole of oxygen gas. Yes, is it clear?
सर एक मिनट थोड़ा सा ऊपर करेंगे.
Yes.
Okay, sir. Thank you.
Next part. Suggest how the ease of decomposition of lead nitrate would compare to that of barium nitrate. Explain your answer. You may find it useful. Refer to the data booklet. Okay. So can anybody know what thing we need to refer to the data booklet?
Radius.
Yes, very good. Radius, because from the radius we can compare which either lead nitrate decomposes more readily or barium nitrate decomposes more readily. The one which have a smaller radius, then the nitrate ion is more polarized and its bond get weaker, so it can be decomposed more easily. So let's have a look at the radius. Okay, so basically this is the latest data booklet, and in this one the radiuses are missing. Mm,
Sir, can't we just use the periodic table?
I think that is not that much beneficial. Let me check. See, here is a barium and here is a lead. Okay, so both are in the same period, and we know that across the period, what happens to the radii? Yes, normally radii decreases due to the more number of protons in the nucleus and the stronger forces of attraction between the nucleus and the electrons. So from here, what we can conclude that the size of lead 2 positive ions is smaller than barium 2 positive ions. Hence, lead nitrate decomposes easily. Is this clear to everyone? Okay. Next part. Barium ethane dioate, BaC2O4, decomposes on heating to produce barium oxide and a mixture of two different gases. Construct an equation for the decomposition of barium ethane dioate. Okay, they don't tell you about the gases. So let's give it a try how it can be. BaC2O4 first we get barium oxide. So if I made a barium oxide, now I am left with C2O3, right? So the other one is carbon dioxide. So I am left with CO only. So the next one is carbon monoxide. So the mixture of two gases and barium oxide solid. It must be solid. Is this clear to everyone? The equation is balanced as well. Is this clear?
Yes, sir.
Okay. Now, next part. an impure sample of BaC2O4 of mass 0.5 gram. Okay, so this is an impure sample. Is added to 50 centimeter cube of 0.2 mole per dm cube acidified magnate. Okay, so it is a volume of a magnate and it is the concentration of the magnate. An excess. Okay, so this is excess. A redox reaction takes place and all the BaC2O4 reacts. Okay, so this indicates that barium ethane diode is a limiting reactant because all of it is consumed. The resulting solution containing unreacted magnate, okay, because it's an excess, so some of the magnate left started with 0.5 mole per dm cube iron to positive ion. Okay, so this is the concentration of iron to positive ion. The endpoint is reached when 30.40 centimeter cube of 0.05 mole per dm cube iron to positive ion is reacted. So here I have a concentration of iron to positive ion, and here I have a volume of iron to positive ion. Okay. Calculate the percentage by mass of BaC2O4 in 0.5 gram impure sample. Show your working. Okay. So 4 marks. Okay. So I have a concentration of magnate. I have a volume of magnate, which is in excess. So I can get the total moles of magnate, which are actually used. So to find the total moles of magnate, what I would do, concentration of magnate multiply by its volume, which is in centimeter cube. So I have to divide it by 1000 to get in dm cube. Now I'll get the number of moles. So yes, can anybody solve it and tell me? So is it
So 1 into 10 is to the power minus 3.
1.0 into 10 raised to the power minus 3, Halima?
Yes, sir.
Okay, so these are the moles of magnate. But remember, these are the moles of magnate which are. Is this clear to everyone?
Yes, sir.
They have further told us, first, there is a reaction between magnate and a BaC2O4, and the leftover magnate is reacted with iron. So secondly, the reaction between the magnate and iron is taking place. If you see here, there is 1 mole of iron and there are, 1 mole of electrons are over here and there are 5 moles of electron are over here. So if I have to find the reaction between magnate and iron, so there must be 5 moles to get the electron balanced. Now if I add both the equations, what would I get? Electrons are cancelled out. MnO4 negative reacts with 5 moles of iron 2 positive in acidic medium, forming Mn2 positive ion and 5 Fe3 positive ions and 4 H2O. So right now I have got the balanced equation for the reaction between iron 2 positive and magnate. What I did, I just added these two equations. But first I have balanced the electrons so I can cancel out these electrons. Okay. I know the volume and concentration both of iron 2 positive. So from that, I can calculate the moles of iron 2 positive. And if you will calculate the mole of iron 2 positive, so it would be the concentration of iron 2 positive ions times volume, that is in centimeter cube. So I have to divide it by 1000 to turns into decimeter cube. Yes, can anybody tell me the answer? Yes, can anybody tell me the answer?
1.52 into 10 to the power minus 3.
1.52 into 10 raised to the power minus 3 are the moles of Fe2 positive, right? And these are the moles of Fe2 positive which are actually reacted with remaining magnate after reaction with BaC2O4, right? So now from this, I can able to find the moles of magnate which are actually reacted with Fe2 positive. So from the equation, what I can see that 5 moles of iron 2 positive are reacting with 1 mole of magnate. So if I divide these number of moles of iron 2 positive by 5, I would get the number of moles of magnate that would reacted with Fe2 positive, right? Or you can say
3.04 into 10 to the power minus 4.
3.04 into 10 raised to the power minus 4, right, Ahmed?
Yes, sir.
So these are the moles that are reacted with Fe2 positive ions, or I can say that these are the unreacted moles of MnO4 negative after reaction with BaC2O4, right? So from this, if you see, I got the total moles of MnO4 over here. I got the unreacted moles of MnO4 over here. So I can find the moles of MnO4 that actually reacted with BaC2O4 by subtracting these 1.0 exponent minus 3 minus 3.04 exponent minus 4. Yes, can anybody tell me the answer?
6.96
Yes, please.
into 10 to the power 4.
6.96 into 10 raised to the power minus 4
Yes.
moles. So these are the moles of magnet that would reacted with BaC2O4, right? What we have to find? our main objective is to find the percentage by mass of BaC2O4. So first I have to find the moles of BaC2O4 and then the mass of BaC2O4. So if you look over here, we got 2 moles and we got 5 moles. So when I compare these two equations, I would multiply this equation with the 5. So it becomes 5, 10, and 10. And this equation with the 2. So 2, 16, 10, 2, and 8. Here it is 16. So now these electrons are cancelled out. And if I add both the equations, I'm going to add it over here. What I get, 5C2O4, 2 negative, reacts with 2MnO4 negative in acidic conditions, forming 10 moles of carbon dioxide, 2 moles of Mn2 positive, right? So if I write this equation over here, 5 moles of C2O4, 2 negative, reacts with 2 moles of MnO4 negative, plus 16 H positive, 10 CO2, 2 Mn2 positive, plus 8 H2O. Now, from this, I can able to find the moles of C2O4 2 negative ion, and that are the moles of BaC2O4 as well. So if I take the ratio, what I find that it is 5:2. This must be X, and here I will write the number of moles of magnet that we have calculated. So can anybody find me the X? Basically, this X is the number of moles of BaC2O4. So X would be equal to 5 times 6.96 exponent minus 4 divided by 2. Yes, can anybody tell me the answer?
1.74 into 10 to the power minus 3.
1.74 into 10 raised to the power minus 3 moles. So I got the moles. Now if I have to find the mass of barium ethane diode, it must be equal to 1.74 exponent minus 3 multiplied by its MR. So here see, they have provided you the MR, that is 225.3. So multiply by 225.3. Yes, can anybody tell me the answer?
Zero 0.392.
0.392 grams. So this is the BaC2O4 present in the impure sample. If you look over here, the total mass of the impure sample is 0.50. I have to find the percentage. So the percentage would be 0.392 divided by 0.500 multiplied by 100.
78.4.
78.4. Okay. Yes, is this understandable to everyone?
Yes, sir.
Okay. Now, barium hydroxide is completely dissociated in aqueous solution. Calculate the pH of 0.12 mole per dm cube barium hydroxide. So if I write the decomposition equation for barium hydroxide, I would get 1 mole of barium ions and 2 moles of hydroxide ions. So if the concentration initially is 0.120 mole per dm cube, then at the end, we would get 0.120 mole per dm cube barium, but 2 times 0.120 mole hydroxide, which is 0.240. Is this clear? So I have got the concentration of hydroxide ions, right? So if I have got the concentration of hydroxide ion, so I can find the pOH, not pH. So if I would take the negative log of the concentration of hydroxide ions, I would get the pOH. So the minus log to the base 10 of hydroxide ion would be 0.240. Okay. Yes, can anybody tell me the answer?
Zero point six two.
0.62.
62.
Okay. So I got the pH 0.62. We know another expression that pH plus pOH is equals to 14. So if I have to find the pH, then 14 minus pOH, and pOH is 0.62. So what would be the answer?
13.38.
13.38. 4 significant figures. So while writing over here in 3 significant figures, it must be 13.4. Is this clear to everyone? So we have completed the 2 questions, question number 115 and okay, 27 marks in almost 1 hour. Okay. Let's move to question number 3. Define the term standard electrode potential. So again, a definition. So I can write, it is a potential or you can say a voltage of a half cell connected to standard hydrogen electrode under standard conditions which are 298 Kelvin temperature or 25 degree Celsius, 1 atm pressure or 101 kilopascal pressure, and 1 mole per decimeter cube concentration of the solution. Is this clear? Now, the three redox systems A, B, and C are shown. The ligand 1,2 diaminoethane is represented by En. Okay. The two electrochemical cells are set up to compare the standard electrode potential E0 of the three half cells. The diagram shows the relative potential of each electrode. Okay. So when this complex is compared with this complex, you would see this is a negative terminal, which means here loss of electron are taking place, which means oxidation is occurring, and that electrons are traveling from this external circuit over here. So here gain of electron is taking place, which means reduction is taking place. Further, what I can conclude that E naught of this cell would be smaller, and E naught for this half cell would be the greater. Is this understandable? Yes.
Yes, sir.
Okay. Now have a look over here. When it is bonded with the water, this is a negative plate. So the loss of electron is taking place over here. So it means oxidation is occurring in this half cell, and the electron that are lost are traveling through external circuit, reaches there. So here gain of electron occur, which means reduction. So E naught for this half cell would be greater, and E naught for this half cell would be smaller. So it means, okay, use this information to complete the table by adding the labels A, B, and C to reduce the order of E naught of the three half cell. Okay, so which one is the most negative one? If you see that having the NH3 would be the most negative one or the most smallest one, which is B. So I would write B over here, and the least negative is water, because water is even here, En would be greater, but when En is bonded to a water, water gets, water gets even more greater. So the water would be A. So A would be here, and C have a moderate E naught value. Is this clear to everyone? Yes.
Yes, sir.
Yes, sir.
Okay.
सर मुझे समझ नहीं आई
Did you understand this part?
यस सर
Okay. So from here, what I can conclude that E of this En complex would be greater than the E of ammonia. Is this understandable?
यस सर
Okay. Now, if you see over here, here we have a water and En, and the half cell of En oxidation is taking place, and the half cell of water reduction is taking place. So the E value of water would be greater than the E value of En,
यस
right? So now if you compare all three, that ammonia is smaller than En, right? and En is
Yes, sir.
smaller than water, right?
ठीक है
Is
सर.
this clear now or not? So on the basis of that, we have concluded that the least negative would be the water. So water is symbolized by A, so that's why we put A over here. And the most negative is ammonia, because from this working, we concluded that the half cell having the ammonia complex, ammonia as a ligand in the complex must have the smallest value, right?
ठीक है sir. Thank you.
Okay. Yes, is this clear to everyone else? If someone have any confusion, do ask. Okay. The complex RuEN3, 3 positive, shows stereoisomerism. The ligand En is bidentate. Okay. The three-dimensional diagram to show the two isomers of ruthenium ethanamide represents the ligand En by using this. Name the type of stereoisomerism. Okay. So if these are three bidentate ligands, there are bidentate ligands and there are 3x means 3, then in this case the isomerism is always optical, and in optical isomerism we always draw mirror images. So how could we draw? Look over here, they have shown you two bonds, rest of the two bonds can be made like this, two bonds going below the plane, two bonds coming out of the plane, and I have to show the isomers. And they have tell me, they have informed us that by this way, I have to show the ligand, right? So see, if I put one N over here and one N over here and connect it like this, so I have put the one ligand. To show the mirror image, I would do the same thing over here, then one N over here and one N over here, and connect them like this to show the mirror image like this. I hope this is understandable to everyone. So this is how we can show the, two non-superimposable mirror image. So they have asked you the type of isomerism. We can write optical isomerism, and these isomers are called enantiomers. Okay, these are the optical isomers, and we can call these isomers as enantiomers as well. Is this clear to everyone? Yes.
Yes, sir.
Yes, sir.
Okay. An electrochemical cell consists of bromine bromide half cell and a silver iron silver half cell. Under standard conditions, use the data booklet to calculate the E0 cell. Reduce the direction of the electron flow in the wire through voltmeter between these two half cells. Okay. So let's have a look at the values first. So for silver, it's 0.8. 0 volt. For bromine, it's 0.107. It's sorry, 1.07. So from this, what we can conclude that here a reduction occur and here the oxidation occur, right? And where the oxidation occurs, the electron are lost. So the flow of electron from the half cell where oxidation is taking place to the half cell where the reduction is taking place. So E0 cell would be E reduction minus E oxidation. E reduction minus E oxidation. So it would be positive 1.07 minus 0.80. Yes. Can anybody tell me the answer?
0.27.
Positive 0.27 volt. And as I have decided that the electrons are flowing from silver to bromine, so I would like from Ag positive Ag to bromine bromide. Is this clear?
Yes, sir.
Okay. Now, water is added to Ag positive Ag half cell in B1. Suggest the effect of this addition on E cell. Place a tick over here. Okay, so see, the equation would like this: Ag positive plus electron Ag, and its electrode potential is 0.80 volt. So if I add the water, what would happen? The concentration of Ag positive goes down by addition of water. And as a result, the equilibrium should shift towards left. And when the equilibrium shifts towards left, this value gets smaller. And if I put the smaller value over here, then the answer of E naught cell would not be this greater than this, right? So it means that E cell gets more positive. Is this clear? Yes, is this clear?
Yes, sir.
Sir, since there's no water in the final equation, so why are we considering it?
Can you repeat, Hamna, please?
Since water is not in the final equation, so why are we considering change of water?
Actually, if you see where when we talk about Ag positive, isn't it aqueous?
Yes.
So initially, if it's a standard condition, then it must be 1.0 moles per dm cube, right? So if I add more water, then what happens to this value? Yes, it's E naught cell, which means that it's a standard condition. So in a standard conditions, the concentration of Ag positive is 1 mole per dm cube. But if I added more water in to that half cell, then what happens to this value?
Decreases.
It decreases. So that's what I told you, that it decreases, and due to decrease in this, as the reaction is reversible, the equilibrium of this half shell shifts to the left. And if this shifts to the left, then this would value would get lower. For example, it gets at 0.75 volt. So if you put this 0.75 volt over here, your this answer would be more greater, right? If there is a still confusion, do ask. Okay. So in explanation, I would write the same thing as I have explained to you, that on adding water, the concentration of Ag positive ion decreases. So the equilibrium, and you have to mention the equilibrium because there are two half equations individually, and each half equation have their own equilibrium. So you must mention that which equilibrium you are talking about, Ag positive Ag shifts to the left. And as a result, the E0 cell, the E cell becomes more positive. Is this clear to everyone? Yes?
Yes, sir.
Okay. I think it's enough for today. We will continue onward from here onward in the next class, okay? Okay. See you everyone in the next class. Take care. Allah Hafiz.
Love, sir.